This session is about defining trial slip surfaces for a slope W analysis. This involves defining the shape and location of the trial slip surfaces. Once again, here is our list of key components. Obviously, a very critical component of an analysis is the trial slip surfaces, defining the extents and the shapes of the trial slip surfaces. Again, we have an entire chapter in our engineering book on trial slip surfaces, chapter number 4, and once again you can go to this chapter for more details. By defining trial slip surfaces, our objective is to find a critical mode of failure and to compute margins of safety or factors of safety against possible failure. This is obviously the ultimate objective of the exercise. When we make the decision as to what is the critical mode of failure or what is the governing factor of safety, we need to look at more than just the factor of safety, as we will discuss elsewhere in these sessions. We also need to judge, you the user needs to judge the physical possibility of a potential failure surface. As you will likely have seen in some of the other sessions, it is not possible to analyze failures or potential failures that couldn't happen in real life. They must be something that could actually really happen in the physical world. And it's up to you to use the user to select trial slip surfaces to represent this situation. Again, you as the user needs to control the position and shape of the trial slip surfaces. When you define trial slip surfaces, you should aim to analyze some specific potential mode of failure. For example, shallow versus a deep failure, or a toe failure, or slip along a weak layer. It is good practice to look at each potential mode of failure separately. It is almost impossible to look at all potential modes of failure with a single set of trial slip surfaces, or for that matter to try and sort out the critical mode of failure with a very wide range of trial slip surfaces that cover many different possibilities. We encourage you to look at each potential mode of failure separately. There are many different ways in Slope W to define trial slip surfaces. The oldest method is what we call grid and radius. It is the oldest one because that is how slope stability analysis first started. Historically, it was the only way to show that many trial slip surfaces had been considered. And as you all know, the objective was to try and get a minimum factor of safety somewhere inside the grid of points. Unfortunately, this is not always possible to achieve. Nowadays, with modern computer graphics and the possibility of computing the factor of safety for many trial slip surfaces very fast, we believe there are better alternatives than the grid and radius for controlling the trial slip surfaces. Nonetheless, because it is so deeply entrenched in slope stability analysis, we maintain the grid and radius option in Slope W, and it is still worthwhile knowing how to use this option because sometimes it serves some specific purpose. Let us go to GeoStudio and open up SLP09, Grid and Radius. As noted here again, originally it was the only graphical means of demonstrating that many trial slip surfaces had been analyzed. You can open up SLP-09, and there are 4 analyses in this file. We'll start with the first analysis called Grid and Radius. Click the All Objects Zoom button. We should be in the Define mode. First of all, we need to go to the Analysis, the Key in Analysis dialog box. And it is in this dialog box that you select the method of specifying trial slip surfaces. As you can see, there's the enter-exit, grid and radius, block specified, fully specified, and so forth. So the option that you select for defining the trial slip surfaces is done as part of the Key in Analyses dialog box. It is also in this dialog box that you must specify the direction of movement. Is it a left to right problem or a right to left problem? It is done in this Key in Analyses dialog box. In this case, we want to use the grid and radius method. Now, we have already defined for you the radius and the grid. However, let us repeat what has been done here. To begin with, once we in the Key in Analysis dialog box have selected grid and radius, then when we say draw slip surface radius, and we select it a second time, what was already defined in the past is now deleted, and we start by clicking, making a box. We click in the upper left corner, the lower left corner, the lower right corner, and the upper right corner. So we have 4 points to make a box. Then we can say we would like 5 increments, say apply, and these are now radius lines. I will click the undo button to go back to where I was for my predefined problem. And what these lines do is they are used to compute the radius of a circle. We can illustrate this with the sketch circle command, and if we have a center of a circle and we expand a circle like this, when it becomes tangent to the radius line, that is one trial slip surface. That's another trial slip surface, another trial slip surface. These are all trial slip surfaces. So the radius lines are simply used to compute the radius of a circle where the center of the circle is one of these grid points. Once again, I will click the undo button to get rid of the circle. And the same thing with the grid. We say draw slip surface grid, click on the upper left, the lower left, and then you have a rubber banded box. You can drag the box such that it creates a grid of points, and then we can make more divisions, creating more points, and each point then becomes the center of a circle. So the number of trial slip surfaces would be the number of points on the grid times the number of radius lines. Now let us go back and to the next analysis, many radius points. And sometimes it is desirable to have a number of trowel slip surfaces that all go through a series of points. We can do this with the same command as before, but the procedure now is we say draw slip surface radius. We click once at the top left, we go down to the bottom left, click the second time at the bottom left, and click where we started, and now we have a series of points. In this particular case, we might have 8 points. In this particular case, all trowel slip surfaces would go through these points. We can illustrate this by going to the results view. In the view preference command, we want to view multiple slip surfaces. Let's say that we view the top 100 or so trowel slip surfaces. And you notice now that all of the trowel slip surfaces passed through these predefined points. Going back to the define view and going to the next analysis, sometimes it might be useful to say that we want all trowel slip surfaces to go through a particular point. Once again, the same procedure. We say draw slip surface radius. We select the point and then we click 4 times. 1, 2, 3, 4. And now we have defined the point, and so now all trowel slip surfaces would go through that point. This is a useful technique by looking at a toe failure, for example, or passing all trowel slip surface through the base tip of a sheet pile wall, for example. Now when we go to the results view, you see that all of the trowel slip surfaces have passed through this one point. Going back to the define view, finally, it is useful to sometimes look at one trowel slip surface. This is particularly helpful sometimes in sorting out problems and looking at differences on different conditions. And so to keep the trowel slip surface at the exact same position, we can have one grid point and one radius point, and so we can say draw slip surface grid, and we click 1, 2, 3, and now we have a single grid point and a single radius point, which results in a single trowel slip surface. Going to the results view, I need to be in my one slip analysis, and in this particular case here we just have one trowel slip surface. You can verify this by saying draw slip surfaces, and you notice that there is only one trowel slip surface that has been analyzed in this particular case. So, a brief overview of the grid and radius and grid method. Still very useful sometimes, but as we saw in the other analyses, the full grid and radius that we had in this case at least achieved the objective of having the minimum factor of safety inside the grid. In a little bit later on in this session, we will see that this is not always the possibility. And many users have difficulty imagining where to draw the radius lines and where to draw the grid, and as a result other procedures have been implemented, I think, that are a little bit more intuitive. Another way to control the shape and position of the trial slip surface is what we call a composite slip surface, and we used the material called impenetrable or bedrock. And when the trial slip surface comes along and hits this material, it goes along the top of the bedrock. This does not need to be a straight line. It can be a multi-bilinear line, as illustrated here. And this is a very useful technique for a slip surface that might pass through a weak layer. Let us go to the file SLP10 to illustrate the idea of a composite slip surface. File, open. Turn off the snap to grid. Click on the All Objects Zoom icon. And in this case, we would like you to draw the radius line. We have shown a sketch line here as to where the radius line should be drawn. So we want all trowel slip surfaces to come parallel to this one line. If we go key in materials, we will notice that the orangey or reddish material is impenetrable. It is a bedrock. That means the slip surface cannot go into this material. So we say draw slip surface radius. In this particular case, we want just one line, so we click twice at the left, 1, 2, and then click twice on the right, 1, 2. We can click now on the Verify button. We see that there are no errors or warnings, meaning that the main solver has enough information to do the factor of safety calculations. So let's click on the Solve button and solve this problem. If we turn on this option here, then the Solve window stays open after it's finished, which is useful sometimes, but then you have to manually close it. So by default, it is usually this checkbox is on so that the Solve window closes when the computing is complete. Now we can go to the Define view, and we see that the slip surface has come down a tension crack, then is on the curved part of a circle, and then follows along the top of the bedrock in the weak layer and then back onto the arc of a circle. It is worth noting here that the radius line can be within the bedrock. In actual fact, the radius line can be outside the geometry completely. It is just a mechanism whereby we compute the radius to create a circle, but when the circle hits the bedrock, then it follows along the top of the bedrock. Sometimes it is useful to use a piecewise linear fully specified slip surface. Let us say that we already know where the slip surface is. For example, we've had some inclinometers and we know where the slip surface is located. Then this can become a fairly useful technique. A few points about this method is that obviously it lends itself only to a very few of trowel slip surfaces. It is good practice to always define the fully specified slip surfaces by starting outside the geometry, and then slope W will compute the intersections. It is better practice than to try and make the point right on the green line. And then simply these are XY points that make up the trial slip surface. So as we show here, these values are computed, and it's best to let slope W compute them. Now, when we have a trowel slip surface like that, we need to have some point about which to take moments, and this is what is known as the axis point. We compute an axis point for you in slope W if you have not defined one. Alternatively, you can deliberately define an axis point. The position of the axis point is not critical when you use a rigorous method like a Spencer or a Morgenstern-Price type of an analysis. Another procedure for defining trowel slip surfaces is what we call the block specified method. We literally define a grid of points on the left and on the right. So here is a grid of points, and here is a grid of points. And then from each point here, we go to every point in the other block. And then at each trowel slip surfaces, there may be a series of projections back to the ground surface. This is a somewhat useful technique, but it also is fraught with some difficulties and has to be used with some caution. Generally, it is not a bad procedure provided this angle is not too sharp and this distance here, the depth should be less than the length. If the depth becomes large relative to the length, then this method can have some numerical difficulties. Let us open up GeoStudio, Slope W, and open up SLP 11. File, Open, SLP 11. Again, clicking on the All Objects Zoom button. We have sketched for you here several boxes which we'll use to guide the definition of the left block and the right block. Once again, if we go into the Analysis key in box under Slip Surface, you will see that in this particular case here, we have selected block specified. Having selected block specified, we then can draw slip surface left block, and we click on the left block and we can control the number of divisions and the projections from the left block back to the ground surface. We say draw slip surface right block, and we can draw the right block. Again, there is our controls here for the number of divisions in the block. Just for illustrative purposes, notice here that we are asking that the projection angle is only 20 degrees on the right and 135 degrees on the left, which brings up a point that all angles in slope W are defined in a counterclockwise direction. So this is 90, this is 180. This would be 45. So angles are defined in a counterclockwise from the 0x axis. Let's go to key in, slip surfaces, left block. Notice that we have a range of projection angles here. the problem called for only one projection angle. Let's make it 135, up to 135, so there is only one projection. Notice that in the drawing now there is only one arrow here. Again, key in slip surface right block. We only want to go at one angle, which is 20 degrees, and the ending angle is 20 degrees, and the number of increments is 1 or none. Once again, notice that on the right block we now have only one arrow. We could now click on the Verify button, and we notice that there are no errors and warnings, and we can analyze this problem and compute the factors of safety. Now when we look at the results view, we can zoom a little bit more into the area of the failure mass. When we say draw slip surfaces, we can click on any one of the trowel slip surfaces in this list box. Alternatively, we can click on any one of the points in the left or right block to give us the factor of safety associated with that particular shape of a slip surface, or we can click back here and say, show me the critical slip surface, the one with the lowest factor of safety. There is a special variation of the block method, and in this particular case we can turn on a switch that says that all points on one level must remain with the points on the other level. This point, for example, would be connected to this point, this point, this point, this point. It would not go over here, not over here, not over here, and would not go to any of the other points. The reason we do that is to try and simulate the sliding along some bedding. So if the blocks are set up in such a way that the base of the block is parallel to the bedding, then we can look at slips that might all follow along the bedding. If we go back to GeoStudio and we go back to the define view, look at the analysis, key in analysis under slip surface, notice that there is this option here. Do not cross block slip surface lines. This option needs to be turned on if you want to use this special feature of the block type of slip surfaces. Another procedure for defining trowel slip surfaces is what we call the enter-exit specification. This is fast becoming one of the more favorite methods of defining trowel slip surfaces, and one of the reasons for this is that it is much more intuitive as to where the trowel slip surfaces should be specified. In a case like this, it is up to the user to specify the enter and the exit area. All slip surface must be either enter in this area here and exit in this area here. So let us open up SLP 12, enter exit, going to GeoStudio, File, Open, enter exit SLP 12. Again, in the define view, under the analysis key in dialog box, slip surfaces. Notice that in this particular case here that we have selected the enter-exit method. Now we have drawn for you with sketch lines where we would like you to draw the enter and exit regions. Let us zoom in a little bit to where we want to draw the enter-exit lines. We say draw slip surface enter-exit. And notice how the cursor now has turned to a plus sign, and the cursor now will become locked to the green ground surface line. It is important that once you click down that you hold the mouse down until you reach the point at the end of the enter zone. Once you release the right mouse button, the definition is complete. We can do the same now. Notice how the cursor is locked to the green ground surface line, and we simply drag to the extent of the exit zone of the trowel slip surface, and when we release the right mouse button, then we have defined the region over which we want the slip surfaces to exit. It is possible to edit these XY coordinates. You might type in 17 meters here and might type in 33 meters here. So these are editable. Also the number of divisions in each one of the zones, plus the number of trowel slip surfaces, say 10 trowel slip surface, 10 trowel radiuses for each trowel slip surfaces. So once again, if we click on the verify button, there are no errors and no warnings, and we can now analyze these trowel slip surfaces. Going to the results view, we see that our critical trowel slip surface now enters within the enter zone and exits within the specified exit zone. It is always useful now sometimes to demonstrate that many trowel slip surfaces have been analyzed in one of two ways. We can use view multiple slip surfaces, and we have to go to view preferences and say view multiple slip surfaces. Let's say that we view the 100 most critical trowel slip surfaces. So with this method, here is one way of demonstrating that you have done many trowel slip surfaces. There is perhaps a better way of doing that, and that is what we call a safety map. We can say view preferences, say show us a safety map. In this particular case, it's often useful to turn off the slip surface shading such that we can see a red band. And what this red band means, we say draw safety map. It means that all the trowel slip surfaces that fall within this red band have a factor of safety between 1.56 and 1.617. Now we can change this range if we made it 0.1 and hit apply. You see now you have a much wider band, so there is a much wider zone in which the slip surfaces between 1.56 and 1.66 fall. Let us go back to decimal 0.5 and apply. Now it is possible to have more than one contour increment, but this is something that is up to the individual. Personally, I don't find this very useful because often these color zones, they are not nicely banded, and as a consequence it is not of great value in my view, but once again, this is a personal preference. The best option is to use one contour increment and apply, and what this does, it draws the attention away that there is only one paper-thin critical slip surface. It says that there is a zone of potential failure in which the factors of safety for all the trowel slip surfaces are very, very similar. There are some other controls on the enter-exit method. It is possible to control the location of the slip surface through a radius command, but I won't take the time here to go into this detail. I'll leave that with you to experiment with. So in conclusion, the enter-exit method we think is a very intuitive method, much more intuitive, but you do need to use some other graphic techniques to transmit the message that you have done many trowel slip surfaces. There is another method of looking at trowel slip surfaces, and if you search the research literature, there are many, many different names for this technique, but it is an attempt to look at slip surfaces that do not have a predetermined geometric shape. The idea is to see if there are trowel slip surfaces that have a lower factor of safety than the ones that correspond to a predefined geometric shape, something like the arc of a circle. We have chosen in Slope W to call this optimization, and the technique is something like this. Once a critical position of a trowel slip surface has been found, then the trowel slip surface is divided into some line segments, and Slope W then moves the entrance point laterally until a potentially smaller factor of safety is found. Next, Slope W then moves to the next point and searches within some elliptical area and moves the point around, again trying to find if there is a factor of safety that is lower than what was found from the critical for the arc of a circle. And so it goes. Next is this point. Once again, it searches in the elliptical area, and these points are moved around, each time looking for a lower factor of safety. Finally, the exit point is moved. Once the lowest factor of safety has been found for each of these point movements, then the procedure goes to the top and starts all over again and goes through all the points. This is computationally very intensive because there are many, many thousands of trials that are done in order to try and find some shape of trowel slip surface that is cannot be defined by some predetermined geometric shape. Now, interestingly enough, the effective optimization does find trowel slip surfaces where the factor of safety is somewhat lower than might be determined for the arc of a circle. So in this particular case, initially we found the arc of a circle, then optimization led to something that is not defined by some predetermined geometric shape. And generally, the factor of safety for this is less than for this one here. And that is the whole object of the purpose of the object, is to try and find a lower factor of safety than that what might correspond to a predetermined geometric shape. Now here is a case where we started out with a block analysis, found the most critical slip surface using a block technique, and then we used the optimization. And notice how the slip surface has become curved. And I think we can all agree that this is much, much more realistic than this with sharp corners. This is not realistic. This is much, much more realistic. Sharp corners don't happen in real life in the field, and it is interesting that the optimization technique seems to reflect that by rounding out the corners. And I think in this particular case, this is a much more realistic factor of safety than something that has sharp corners. Now we can go to GeoStudio and open up SLP 13. Going to the Define view, File, Open. In this case, we have analyzed this problem using a block sliding technique, and then if we go to the Key in Analyses dialog box under slip surface, we have checked this box here saying that once you have found the critical slip surface using the block method, then do an optimization on that particular slip surface. And if you go to the results view, notice that we can look at the optimized slip surface and we can look at the non-optimized slip surface. So this was the slip surface without optimization. This was the slip surface with optimization. Interestingly, again, notice how the sharp corners have been rounded off. The factor of safety is not all that different, but it is slightly lower, but perhaps the slip surface shape is somewhat more realistic with rounded corners than with the really sharp corners. If you are going to use the optimization technique, we do not have time here to go into a lot of detail, but generally, the optimized solution should be quite similar to the unoptimized solution. There should not be a great difference in the factor of safety. If the difference in factor of safety gets to be too large, then it becomes questionable whether the optimized solution is realistic. It is true that under certain conditions the optimization technique can get lost and produce unrealistic results. So the method has to be used with some thought and caution. Sometimes it obviously, as in this case, results in a more realistic slip surface, but there are cases where you as the user you have to dismiss the optimized solution if it becomes unrealistic. There is another important component to specifying trial slip surfaces, and that the position of the critical slip surface is related to the soil strength properties that you have specified. A very common situation is analyzing the case for purely frictional material. In other words, phi is greater than 0, but cohesion is 0. And in this particular case, it turns out that when you do that and you have, for example, a grid and cohesion is 0, then the critical slip surface will be somewhere on the edge of the grid. And the tendency then is to move the grid. But once again, the critical is on the edge of the grid. And then we move the grid, and the critical again is on the edge of the grid. The reason that this happens is that theoretically the correct solution is when the radius is at infinity, or in other words, the solution tends toward the infinite slope case. So in this case, when C equals 0, the factor of safety simply is tan phi divided by tan alpha, and the radius tends toward infinity. This is rather difficult for a lot of people to accept and to handle at first, but indeed, if the soil truly does not have any cohesion, then this actually does represent real life and the actual case in the field. If you were to take a fine dry sand and drop this sand from a funnel and allow a cone of sand to build up, you would notice that the cone increases in height by always slipping on the surface. Always the grains, they slide and roll on the surface. You see this actually also in the field with stockpiling granular material. The height of the pile always increases by slippage on the ground surface. So, slope W, by tending toward the infinite slope case, is actually representing real physical behavior, and slope W matches what's happening in the real physical world. So how can we deal with this case? Well, let us go back and open up SLP 14. SLP 14, and there are two analyses in this particular problem. And we can go to the results view, and we notice that in this particular case here, we have zero cohesion. Here's another feature of GeoStudio. Say View, Object Information. Soil or material colors are displayed. We can say View, Object Information, click on this region, and notice that this material has zero cohesion. Turn off the material color, and you of course notice that the critical slip surface is essentially parallel to the slope. And in this particular case, the factor of safety then would be tan phi divided by tan alpha. Now, in actual fact, in all likelihood, in almost all field cases, the cohesion is not exactly zero, and as a result, we are not analyzing a realistic case. If we go back to the define view and we select the stability with suction, and in the strength session that we talked about, we showed how to include suction strength in the analysis. In this case, when we say key in materials, and we have a middle layer here with suction, under the suction tab we have defined a volumetric water content function. As a result, we are including a little bit of suction strength in the unsaturated zone, and as soon as we do that, then we of course see that the critical slip surface is at some depth because we have included a little bit of strength which is representative of some strength in the unsaturated zone. If we say draw a graph and we show the suction strength and the cohesive strength and the frictional strength, we can see that in this particular case here there is just a little bit of suction strength, and when we include this component, then the critical surface is the critical slip surface is no longer parallel to the slope. The question then is how to handle shallow slips. Well, there are many different ways of doing it. We could assign soil near the ground surface a small cohesive strength component representing a desiccated layer or a plant root zone. There is an option in Slope W to specify a minimum depth for the slip surface. The downside of this is that the critical slip surface still is on the edge of the grid, even though you have forced the slip surface to be at some depth. By doing this, we are indirectly saying that there is some strength near the ground surface, but rather than including it physically, we would just simply arbitrarily keep the slip surface at some depth. There is also, I showed how to include a suction strength. At this stage here, if you are interested in more details, I would suggest that you go to the engineering book on page 109 and 110 for more details. Now we have the pure undrained case, and we have the opposite situation. When phi is 0 but cohesion is greater than 0, we have the undrained case. The slip tends to be very deep. And what happens sometimes when you have a grid, then the minimum tends to be at the bottom of the grid, and then the urge is to move the grid down, and pretty soon the grid is below the crest of the slope. This is for the purely undrained case, where the strength is a constant with depth. What is the solution to this problem? Well, generally, the solution lies in an unrealistic strength profile. Strength never, if seldom or never, is constant with depth, and it is much more realistic to specify an undrained strength that increases with depth, and that avoids the critical slip surface from going very deep. To drive home the point that the position of the critical slip surface is a function of the strength parameters that you choose, take a look at this particular case here. We have the exact same factor safety for the two cases. C and phi are different, but notice, even though you get exactly the same factor of safety, that the position of the critical surface is vastly different. So the critical point here is that the position of the slip surface with the lowest factor of safety is a function of the strength parameters that you can choose, The most realistic position of the critical slip surface is obtained when you use effective strength parameters, effective cohesion intercept, and an effective phi. And together with the effective strength parameters, you use a realistic definition of the pore pressures, including suction if necessary. So to repeat, the most realistic position of the critical slip surface is obtained with effective strength parameters. There are several other means of controlling the shape of the trowel slip surfaces. One of them is to specify and incorporate tension cracks into the analysis. There are several different ways of defining a tension crack. We list 3 of them here. One of them is to specify an inclination angle. And so If the slip surface becomes too steep, then an angle is specified, and if the slip surface becomes too steep, a tension crack is automatically incorporated into the analysis. A second way is to specify a constant depth. If you have a slope like this, simply to say that this is the tension crack depth. There is a third way in slope W, but we recommend that you not rely on this method. When we first thought of this idea, it seemed like a good idea, but later we have changed our mind about this option, and as of the current version, we recommend that you not use this option. The reasons for this we do not have time to explain here, but just accept the fact that we do not recommend that you use this option in slope W. In fact, in a future version, we may even remove this option from slope W. We suggest you use one of the other two methods to define a tension crack. To see how this is done, let us go to GeoStudio and open up SLP 15. I have already opened up the file. There are two analyses in this file, a no tension crack analysis and a tension crack analysis. And what we need to do here is to define the tension crack. But before we do that, let's look at the results view with no tension crack. And we see, of course, here that there is no tension crack in this particular case. Well, let's go back to the define view. Let's go to the second analysis with a tension crack. Going to key in analysis, and under the slip surface tab, we see that currently no tension crack option is specified. We want to specify that we want to make use of a tension crack line. So we need to select that option. Notice that there are other controls here about having to do with water in the tension crack. I won't take time to dwell on that here. I think this is self-explanatory and you can discover the effects on your own. Having selected that option, we can turn on the Snap to Grid and then say Draw Tension Crack Line. And if we were to say that the tension crack is 3 meters deep, we can simply draw a line across the section which gets crosshatched, and that now then becomes the tension crack depth. And if we go to the Solve window, save the problem, and rerun analysis number 2, and go to the results view, you see that now a tension crack has been incorporated into the analysis. That is all I am going to illustrate about tension cracks in this particular problem. Let's go back to the PowerPoint presentation. And as we have illustrated here the two different methods, this is the tension crack line. Here is an illustration of what it looks like when you specify an inclination angle and the slip surface angle gets too steep, then slope W automatically incorporates a tension crack. Personally, this I believe is the best way to do it. It's a tension crack that is of variable depth depending on the shape of the trowel slip surfaces, but once again this comes down to a personal preference as to what you wish to do and how you wish to define a tension crack in a slope W analysis. Another slip surface control is that we can specify the entrance and exit projections of a particular slip surface. This can be quite useful to simulate things like passive earth pressure conditions or active earth pressure conditions. We can illustrate how this is done by looking at a footing bearing capacity problem. Let us open up SLP 16. File, Open. SLP 16. Clicking on the All Objects Zoom button. Taking a look at the analysis tree. We just have one stability analysis. Under slip surfaces, we want to use enter-exit as a means of specifying trowel slip surfaces. We can say draw slip surface, enter-exit. We are going to force all trowel slip surfaces to enter the ground at the outer edge of the footing, and then we will allow the slip surface to exit over a various distance to the right of the footing. Let's make this, say, 10 increments. But notice now that we have checked this box, and we have said that the passive portion of the slip surface should be projected at an angle of 30 degrees. The projection angle is indeed actually illustrated here, so that there is a graphical clue as to what has been specified. Now in this particular case, I'll show you one other thing, and that is to say draw slip surface axis point. The axis point by default will be drawn too low in this case, so I will simply select the axis point somewhere here. It does not really matter if when we do a Spencer or a Morgenstern Price method, the location of the axis point does not really affect the factor of safety, but I want to display the factor of safety at some convenient point. If we click on the Verify button now, we see that there are no errors and no warnings, and we should be able to compute a factor of safety here. If we now go back and look at the results view, we see that indeed the slip surface is projected at an angle of 33 degrees. This is 30 degrees. We can verify this in another way by saying View, Slice Information, and if we click on one of these slices that are close to the toe, we notice that the base angle is 30 degrees. Base angle is 30 degrees, as was specified. So this is a simple illustration of another trowel slip surface control. In summary, we can control by a specified projection angle for the passive end of the slip surface and for the active end of the trowel slip surface. This then brings us to the end of the session on defining trial slip surfaces. It is important to realize that defining the trial slip surfaces is not a black box. It requires some thought from you, the user, and some user guidance. You, the user, you have to think a little bit ahead as to what mode of failure am I trying to analyze, and then to guide Slope W with possible but realistic trial slip surfaces. Once again, an extremely important observation is that the critical slip surface depends on material properties. Different material properties can give different locations of the critical slip surface. Once again, multiple potential modes of failure may exist in one problem. We would encourage you to look at each one of the modes of failure separately, which is now quite readily done with multiple analysis in the same file in Slope W. So this then brings us to the end of the session on trial slip surfaces for a Slope W stability analysis.